Welcome students. Now we are going to learn about complex integration. The uses of complex integration are this complex integration is a method in complex analysis. It has various applications across diverse fields, particularly in engineering and mathematics. It involves integrating complex value functions along paths in the complex plane, often using techniques like contour integration and residue theorem. This approach of complex integration is valuable for evaluating integrals, solving differential equations, analyzing systems in areas like electrical engineering, fluid dynamics, and signal processing. Topics we are going to discuss in this module is line integral, Cauchy's integral theorem, Cauchy's integral formula, application of Cauchy's integral formula, Taylor's and Lorentz expansion, singularities, poles and residues, Cauchy's residue theorem, and evaluation of line integrals using Cauchy's residue theorem. So, what is line integral? We all know we have studied the analytic functions in the prior sessions. So, we all know what is complex variable z equal to. It can be written as x plus iy. Now, if w equal to f of z be a continuous function of the complex variable z equal to x plus iy along the curve C with endpoints A and B, then integral over C f of z into dz can be evaluated from f of z, separating the real and imaginary part, and multiplying it with dz, you are getting u dx minus v dy plus I times v dx into v dx plus u dy. Now consider this problem. Evaluate integral over the contour C, z bar into dz from the path joining the points 0, 0 to 4, 2 along the curve C, and z is given as t square plus it. Here we have to find what is z bar and multiply it with dz over this path we are going to evaluate it. We all know what is z equal to is x plus iy. That way in the problem it has been given as t square plus I into t. Now equating this real and imaginary part, we are getting x equal to t square and y equal to t. So put x equal to t square in z bar and y equal to t. Therefore you will get z bar is equal to t square minus I times t. Now what is dz? D is a derivative of z that can be written as dx plus I times dy. From this, dx is equal to 2 times t into dt and dy equal to dt. So substituting here and doing the simplification, we are getting 2t plus I times dt. We have to know, now we have converted everything in terms of the parameter t. Therefore, we have to find out what is the range of t along this path. So to find that, here we know that x equal to t square. By taking x equal to 0, this x equal to t square will become t equal to 0, 2. When y equal to 0, we are having y equal to t. From that, we are getting t equal to 0. When y equal to 2, we are getting t equal to 2. So, if we can observe from these two, t is ranges from 0 to 2. Substituting t is ranges from 0 to 2 in z bar into t z and evaluating it, you are going to get this going to be integral 0 to 2, okay, 2 into t cube plus I into t square minus 2I into t square minus I square is minus 1, so plus t into dt. By doing the integration, you will get 2t power 4 by 4 plus I into t power 3 by 3 minus 2I into t power 3 by 3 plus t square by 2. Apply the limits 0 to 2. So here 2 into 2 power 4 will give you 16 divided by 4 plus t cube is 2 cube 8 by 3 into I minus 2I into 8 by 3 plus t square is 4 by 2, which gives you, here you can cancel 4 times, therefore 8 plus here 8 by 3 into I, this is 2 times I into 8 by 3, so minus sign we are getting, therefore we are going to have this plus will become minus sign, minus sign 8 I by 3 plus 2. By adding these two, you are going to get 10 minus 8 I by 3. This is the answer we are getting here. So this is simply the line integration over the complex plane. Now next we are going to learn about what is the connected region. A connected region is a region which has no break at all. So a region R is said to be connected if I am considering any 2 points of it, they are connected by the curve. The curve should lie inside the region. Therefore, we can say that the region is connected. What do you mean by simply connected region? A region is said to be simply connected if any closed curve which lies in R can shrunk to a point without leaving the region. This is called a simply connected region. Multiply connected region means a region which is not simply connected is called multiply connected, but this multiply connected can become a simply connected by doing the cross cuts here. You can do the cross cut here, you can do the cross cut here, here also you can do the cross cut, so that you can able to bring all the multiple regions into a simply connected region, that is a region which can be shrunk to a point. Based on these primary definitions, we are going to see what is Cauchy's integral theorem or Cauchy's fundamental theorem. This states that if f of z is analytic and its derivative f dash of z exists and are continuous at all points inside and on a simple closed curve, then integral over c f of z into dz equal to 0. Cauchy's integral theorem for multiply connected region, it says that if f of z is analytic and its derivative f dash of z is continuous at all points in the region bounded by simple closed curves c1 and c2, then integral over c1 f of z into dz minus integral over C2 f of z into dz equal to 0. So that gives you integral over C1 f of z into dz equal to integral over C2 f of z into dz. Next, we are going to see Cauchy's integral formula. If f of z is analytic inside and on a simple closed curve C that encloses a simply connected region R, and if A is any point in R, then f of A equal to 1 by 2 pi I integral over C f of z by z minus A into dz. So from this formula we can able to write integral over the closed contour C f of z into dz by z minus A into dz equal to 2 pi I into f of A. So by making use of Cauchy's integral formula, we can able to find out the value of the integration if the point A lies inside the simply connected region R, then 2 pi I into f of A, where C is described in anti-clockwise direction. So the generalized formula for Cauchy's integral is if a function f of z is analytic within and on a simple closed curve and A is any point lying in it, then integral over C f of z into dz by z minus A to the power n plus 1 equal to, you can write it as integral over the closed contour C f of z by z minus A to the power n plus 1 into dz equal to 2 pi I into f n of A by n factorial. Here f power n of A denotes, okay, the nth derivative of f of A, nth derivative of f of A. So here when you are having the power of z minus A is greater than 1, okay, the formula of integral over C f of z by z minus A to the power n plus 1 into dz is 2 pi I by n factorial into f1 of A. This is by using general Cauchy's integral formula. Now consider this problem. Evaluate integral over the closed contour C dz by z square minus 7z plus 12, where C is mod z equal to 3.5 using Cauchy's integral formula. So here first we have to identify what is this mod z equal to 3.5 represents. We all know what is z. Z is x plus iy. So modulus of z can be written as z into z bar. Here z bar is what? X minus iy. Now by doing the product of x plus iy and x minus iy, we are going to get x square minus ixy plus ixy minus I square is minus 1. So already minus sign is there. So plus y square. That's why these two gets cancelled. We are going to have x square plus y square. If I am taking, yeah. So modulus of z equal to 3.5. Here this z square, modulus of z square is z into z bar. So you can able to get modulus of z square equal to x square plus y square. If suppose I'm having modulus of z alone, you have to take under root of x square plus y square. So here given that modulus of z equal to 3.5, it refers, it is a circle, implies that what? Under root of x square plus y square equal to 3.5. So taking square on both sides, you will get x square plus y square equal to 3.5 the whole square. What it represents? It represents a circle with center 0, 0 and radius is equal to 3.5. Because of that only, here you can see the picture having x and y axis, and we are having the circle with center 0, 0 and radius is 3.5. So here, for evaluating this integration by making use of Cauchy's integral formula, you have to identify that what are the singular points lying inside this contour mod z equal to 3.5. To get the singular points, we have to equate the denominator of the function to 0. Singular point means a point at which z equal to z0, at which f of z fails to be analytic. Fails to be analytic means that does not exist derivative. So for finding the singular points, okay, singular points, you are equating the denominator to 0. By equating the denominator to 0, you are going to get z equal to 3, 4. Now we have to identify that whether the point 3 and 4 lying inside this contour C. So what is z equal to 3? The meaning of z equal to 3 is x plus iy equal to 3. That means by equating the real and imaginary point x equal to 3 and y equal to 0, or it refers the point 3, 0. So at the point 3, 0, if we are marking the cross, you will get z equal to 3 because the radius is here 3.5. So I am taking the point z equal to 3 as this place. Then likewise, if you are seeing z equal to 4, it refers x plus iy equal to 4. So this 4 can also be written as 4 plus I times 0. So we are getting x equal to 4 and y equal to 0. From this, you will get the point as 4, 0. So z equal to 4 refers the point 4, 0. So we can draw the point z equal to 4 here. Now you can easily observe that by plotting the points in the circle, you can easily observe that the point z equal to 3 lies within the circle and z equal to 4 lies outside the circle. Therefore, we can able to evaluate this integration by using Cauchy's integral formula only at this point. Now, we are going to consider the point which is lying outside C, okay? We are going to club it with the numerator. So the numerator is going to be what? 1 by z minus 4. This we can take it as f of z. So f of z divided by z minus 3. Here the point 3 is the singular point lying inside the circle 3. Inside the circle mod z equal to 3.5. Okay. Now, according to the Cauchy's integral formula, we are going to have this as what? Integral over C by Cauchy's integral formula. Integral over the contour C, okay, f of z by z minus a into dz equal to 2 pi a into f of e. So this implies that integral over the closed contour C, okay, here C is mod z equal to 3.5, f of z, okay, divided by z minus 3 into dz equal to 2 pi I into, okay, f of a. What is a here? 3. So what is f of z? 1 by z minus 4. Put 3 there, you will get 2 pi I into f of 3 gives you 1 by minus 1. So it is going to be minus 2 pi I. This is the answer. Hope you all understood. So for evaluating the integration by making use of Cauchy's integral formula, first you have to find out the singular points at which the function fails to be analytic, and you have to check out whether the singular points lies inside the contour. At those points you are going to make use of Cauchy's integral formula and do the evaluation of it. Thank you.